Chapter 29, we stopped looking at discrete random variables and look at the continuous random variables, so measurable random variables. And a continuous probability density function, PDF, is a function such that f of x is greater than 0 on some interval a to b, and the integral of f of x from a to b is equal to 1. That is, the area under the curve is equal to 1. And we can find probabilities by finding the area under this curve. For a continuous probability density function, the mode is the maximum value of f of x, the most probable. The median is the solution to this integral, the integral from our start value to some median value of that function is equal to 1/2. Should make sense, the halfway point of the curve. And the mean can be found by finding x times f of x, the integral from a to b. And the variance is integral from a to b of x squared times f of x dx minus the mean squared. And these formulas should look pretty familiar from last chapter. We're just applying a continuous perspective on these formulas from the discrete random variables. So here we have a function. We're equal to 1/2 x when x is on the interval from 0 to 2, and it's equal to 0 everywhere else. Is this a probability density function? Well, let's take a quick look at the graph. One half x has a y-intercept of 0 and a slope of 1/2, so up 1 over 2. So there is our curve, and what we're wondering, well, all of the function values are greater than 0. That condition is satisfied. Question would be, what is this area? This is equal to x squared over 4 evaluated at from 0 to 2. And this area under the curve is equal to 1. We could take a geometric approach with this particular function because the area is just a triangle. But now we need to find the mean, the median, and the mode. To find the mean, we're going to be taking the integral from 0 to 2 of x times f of x. So it becomes 1/2 x squared dx. And this would be equal to 1/6 x cubed evaluated from 0 to 2. And that's equal to 4/3. So the mean value is 4/3. The mode is the maximum point. So the maximum point here is at x equals 2. The median, we look at the integral from 0 to some m value, which is the median of the function. And we want to know, when does that equal 1/2? So we have 1/4 x squared evaluated from 0 to m equals 1/2. So we have 1/4 m squared equals 1/2. And we can solve this and get m is equal to the square root of 2. The median value is square root of 2. The last thing that we need to find here is the variance. And that was equal to the integral from 0 to 2 of x squared f of x minus the mean squared. So 1/2 x cubed, that's x squared f of x, minus the mean squared. So minus 4/3 squared. Our variance equation becomes 1/8 x to the 4th evaluated from 0 to 2 minus 16/9, and evaluating this we end up with 2 minus 16/9. That's 18/9, take away 16/9, or the variance would be 2/9. And from that we could find the standard deviation as well. Now there is a special type of distribution called the normal distribution. It's bell-shaped, and this distribution is symmetric around the mean. And for a perfectly normal distribution, the function that defines this curve is defined by this formula right here. And it can be found that the integral from negative infinity to infinity of this function is equal to 1. The area under the curve is equal to 1. And these represent probabilities. And we can find the function value of the mean by simply evaluating this coefficient of e. Because if the x value is equal to the mean minus mean is 0, this exponent becomes 0, so e to the 0 is 1. And we're going to skip that part for the time being. And we're going to look at application of this. In that diagram that we just had, it shows us that one standard deviation of the mean either way, 34.1% of the data above and 34.1% of the data will fall below the mean. Within the next standard deviation above and below, there's 13.6% of the data. And further than that, within 3 standard deviations, there's another 2.15% of our data found within 3 standard deviations. So within 3 standard deviations of the mean, there's 99.7% of all of our data. So here we have chest measurements. They're found to be normally distributed with a mean of 95. So in the center of this bell curve we have 95 and a standard deviation of 8. So one standard deviation above the mean would be 103. Another one would be 111. 3 standard deviations would be 119. One standard deviation below the mean would be 87. Another standard deviation below, 2 standard deviations below the mean, that would be 79. And 3 standard deviations below would be 71 centimeters. Now it's asking us to find the percentage of the data between 87 and 103. Well, that would be represented by this area, and that's 1 standard deviation either way. And if we go back to our picture here, there's 68.2% of our data within 1 standard deviation. Between 103 and 111, if we go back to that picture again, there's another 13.6%. That's this purple area. So the probability that a randomly chosen male is between 87 and 111, we can add these two areas together. And what we get is approximately 81.8%. And depending on what table or book you look at, these percents might be slightly different depending on the rounding that was done. On the graphing calculator, we can use these two notations, the normal PDF, the normal CDF. Using this distribution notation that we've seen with the discrete random variables, we can say that X is normally distributed with those two parameters. The mean is 10, the standard deviation is 2. What we're putting in the parentheses is the mean and the variance in this notation. In the calculator, we would put in the random variable that we're looking at and the mean and the standard deviation, or if we have a lower limit and upper limit. Now if we're dealing with infinity as one of the limits, the way we put infinity into the calculator is we use scientific notation. And the way we put negative infinity is similar. But we want negative 1 times 10 to the 99th. So if we're evaluating less than, say, 45, we would put negative E99 for that limit, the lower limit, and 45 for the upper limit, and then the mean and standard deviation if we're doing it in our calculator. Tomorrow we will look at how to use a table of values to figure out these probabilities, these areas under the curve also.